I have recently published a set of videos regarding Einstein's PhD dissertation. That dissertation was an inspiring piece of research, let's say, even if it is not as well known as other articles written by Einstein. Also remember that thesis or dissertation, whatever you want to call it, was written in 1905. It was published in 1905. And does that ring a bell? Well, it should, because it is Einstein's miracle year, where he published other 4 papers on the Brownian motion, the photoelectric effect, special relativity, and also on the famous equation E equals mc squared. So he really did produce amazing content in that year, marvelous year. But he also published this thesis, this dissertation, and this dissertation revolved around a different calculation, a different method of calculating the size of molecules. It was not really, let's say, something written in the stone. There was still speculation about the size of atoms, and in particular when we go to very small scales. That was not, as I said, written in stone. But anyway, Einstein did find a new way to calculate the size of atoms, to estimate it. And he used, incredibly, solutions. And when I say solutions, I mean a solvent and a solute. So I'm talking about a liquid and small particles suspended in this liquid. So we have a solution. And then he used the equations of hydrodynamics, which means Navier-Stokes equations. That's incredible if you think about it. And then he went through some very difficult calculations. And when I say very difficult, actually, I mean that they are quite involved. There is a lot of calculations, and it's not even easy to follow all the calculations. But if you want to know more about the details, you can check the videos that I have published, where I perform all the calculations, which are not contained in Einstein's paper. So I have made the calculations myself, and I have proposed the same method that Einstein used, and you can find that method on my channel and also in one of my courses online, in particular Partial Differential Equations. And I have put this content into that course because, of course, we are talking about the solution to Navier-Stokes equations, which are partial differential equations, right? Anyway, Einstein starts from Navier-Stokes by considering first a small sphere suspended in this liquid, and then he goes through a bunch of calculations, and also he generalizes this theory to more spheres, which are small particles. So he thinks about small particles, spherical particles, inside this liquid, and then he makes some calculations to find, in particular, the work, or I should say heat, produced inside this liquid. And from the heat, he managed to find the relation which contains also the viscosity coefficient. Then Einstein also does a different calculation, still regarding the heat produced inside this liquid, and he finds another relation that takes into account the friction coefficient with the spheres in it, with the particles. So he manages to find an equation which on one side contains the viscosity coefficient of the liquid without particles, and then on the right another part of the equation which contains the friction coefficient of the liquid with the particles. So he finds a relation between these two coefficients, which also contains the number of particles per volume, and in particular also the size of these particles, which is the radius of the sphere. And then he uses also diffusion, because these particles will involve a so-called osmotic pressure. What's osmotic pressure? Well, when I have a bunch of particles concentrated in some part of the liquid, if I want to keep them there, I need to exert some pressure, because otherwise these particles will tend to go from a high concentration to a low concentration. That's the idea. And the diffusion equation will contain both the Avogadro number and also the size of particles, the radius, and also the equation that I mentioned earlier, the one that relates the two friction coefficients, the two viscosity coefficients, one with the spheres and the other one without the spheres. It also contained the Avogadro number. So Einstein used these two equations to find both the Avogadro number and also the estimation of the radius of the sphere. And he finds some results that were not that bad, but they were not even that good, because without even realizing this, Einstein had made some mistakes in the calculations. not in the reasoning. The reasoning was flawless, but the calculations were wrong, and he missed a factor of 2.5 actually in one of the coefficients. And he realized this after some years, because a researcher with the name of Perrin made some experiments and he found some discrepancy between his results and Einstein's predictions. But then Einstein asks one of his students to redo the calculations, and after he understood that there was a mistake, he published a new paper correcting these calculations. And the results this time were very good actually for the time. So that's basically how Einstein got his PhD. His thesis was quite short because it was about 24 pages, and nowadays of course we cannot publish such short PhD dissertations, unfortunately. Anyway, Einstein also tried to get his PhD in 1901, so 4 years earlier. But his thesis was not successful. He tried 4 years after, and he finally managed to obtain his PhD. His work was also commended by one of his reviewers. Professor Klein was one of them. He commended Einstein's work, saying that he had a great mastery of the hydrodynamics equations, which are some of the most difficult equations in physics. And it is still true nowadays in some sense, because there is also one of the Millennium Prizes regarding this set of equations. But indeed it's true, Einstein showed a great mastery of these equations.